the problem. So we are going to model the process as the producer and consumer problem. We simplify such a problem. Like somebody produce, make the data, somebody use the data. So produce and the consumer problem. So we are going to use such a producer and consumer problem to understand the race condition. So this is the exactly same example as what I explained just before. So we have the two processes. One is the plus, counter plus, the increment. The other one is a decrement. Okay? So let's say that we have the two CPU like this one. Then the memory, we have the shared data here. And at the time, the reason is that this command is a high-level language. Eventually, it will be changed to the assembly language. So in terms of assembly language, it's like the 3-step, the 3 instructions, like the read the data using move. Okay, we can use the move the instruction. So move from here to here, save the register one, and we can increment. We can use the INC, or depending on the CPU, maybe different name of the instruction, but basically increase. And write back, move the register information to the shared memory using the move instruction. Similarly, count to minus is this one. So because of that, even though we run the same time this one, the instruction by instruction. So instruction is the only the minimum level of the command. Okay, we cannot break into two parts of such an instruction. So this is an example of the assembly language. Okay, the machine language to explain about this one. So you already know the basic. So there are different cases. Like roughly, we can say the 3 different cases that I explained. So I don't have to go through all of this. Finally, one of the examples is a counter is a shared data going to 4. This one. Another one is the 6. Okay. So also 5 is possible. So this is called the example of the race condition synchronization problem. So to address this one, we operating system side, operating system perspective, we are going to define the process as the critical section and the remainder section. Critical section means a set of instructions that would like to access shared data. And the others are considered as a remainder. So that before operating system allow process execute the first instruction of the critical section, this part, the operating system run the entry section. Similarly, when the operating system CPU right after execute the last instruction of the critical section and operating system run the exit section. It's the additional code. Okay, additional code of the provided by the operating system. So this is the diagram to understand the critical section. What we are going to do is we try to the code entry and exit section to solve the problem of the synchronization. Okay. Then what about you have the 2 process? If you have the 2 process, like we have instruction process I and process J, or the 0 or 1. So we have the instruction. We have instruction. They are not identical. Okay? But this one access I value, okay, read I. And this one somewhere here read I. But the other part may be different. So at that time we consider this instruction as the critical section, and also this is the critical section. So when operating system realize the instruction need to access the shared data, critical section, then the operating system execute the entry section code and exit. This entry and exit section is the same as any process. Entry and exit. This part, critical system, may be different, but they are accessing the shared data. And the other part may be different. It doesn't matter. Okay? It's a remainder. But the entry section, exit section is not coded by the U. Sometimes application program itself need to take care of synchronization problem. We will see such an example in the semaphore later. But right now, we are going to consider the synchronization problem by the operating system. So operating system provides this one. So we are going to see what is the algorithm of this one. It's kind of simply selection process. Okay, that makes sense. Like think about the advising. So you'd like to see your advisor, professor, but usually there might be long queue. Okay, so you are going to wait outside of you cannot see the process. The 2 or 3 students see the professor same time. No, it's not possible. Only one student. So there might be usually you are using the queue outside waiting, but sometimes some of the students need just a signature. Okay, so we can consider such a priority or the timing to see the professor. So that is kind of the entry and exit. There is a kind of selection process and the next process. So this is one of the simplest solution. You don't have to worry about it right now. We will see it later. So the reason why do while the outside is keep working. So operating system keep watching whether process instruction access the shared data. In case the critical section, run this module, and no matter how many processes you have. Okay, so before we discuss about the algorithm, that solution satisfies a certain condition. Whatever the solution we have, we need to consider the basic requirement. Think about going to the bathroom. How many people can use the bathroom at the same time? Only one, which means it should be always mutual exclusion. You cannot share the resource. Okay, only one. That makes sense. So that is the first requirement, mutual exclusion. Okay. So but understanding second and third is not the simple. So second is progress. Progress means I'm waiting outside. Eventually, no matter how many people are waiting outside of the bathroom, they eventually use the bathroom. Otherwise, if there is no chance to use the bathroom, you will be died. So eventually, but the problem is, sometimes it may take a time, 1 hour, 2 hours, but eventually, so which means if one of the students cannot use the bathroom, keep waiting, which means it's a deadlock situation. Okay, something wrong. So I'm not going to explain the details of deadlock right now because we have a separate chapter. That's another big issue in the operating system. So we will talk about that deadlock in chapter 7. So I think the week after week. So after the 2 weeks later, we will talk about. But intuitively, you understand what is a deadlock. Okay, something stopped. So I'm waiting outside the bathroom, but something wrong. So I never get the chance. So that should not be happen. Eventually, that is a progress. So more precisely, we can define such a process requirement is no process is if no process is executing in its critical section, which means there is no process, there is no one in the bathroom. Then some process wishes to enter, which means if somebody wait outside, then only the process that are not in IC, which means only process in the entry section who are waiting outside that decide the next one. Okay? If you are waiting outside of the bathroom, those people will decide. That makes sense. If he doesn't want to use the bathroom, if he's selected because he's very close of my friend, just like they are not, they will not have the chance to enter critical section. So only among the people outside, okay? can decide the next process that the process, that selection will not be postponed indefinitely, which means should not be forever. Okay? Limited the finite time that selection should be done. In other words, simply it's not deadlock situation, deadlock free. So that is called the progress requirement. So eventually, if you are waiting outside, sometimes later you will get the chance. Then the bounded waiting time is starvation free. So that selection will be happen forever. Problem is if he's not selected, so he's always in the outside. But that selection, so it's a forever because they decide by it, but he's kind of the isolated person. Nobody selected him, so he may not get chance. Okay, so that selection should not be the forever, which means starvation free. Starvation means what? You do not get the chance of the research. Starvation usually happens like the priority-based approach. So we have the priority of the student. So priority 0, 1, 2. So if I consider the highest priority student only, lower priority will not get the chance. That is a starvation. So we need to, that happens a lot in operating system. We will see later, such as the starvation problem in deadlock situation also. So that is a starvation free. Bounded waiting means it's a limit, the finite number of times you can wait. Okay? So eventually, so the idea of the progress and the bounded waiting is eventually the process who is waiting, the critical section will get the chance. Okay? Because it's a shareable data. If you do not consider, you can easily understand mutual exclusion. Only one process can access one data. Okay? However, if you are using just a key outside, so if you do not have the algorithm, logic, like make the one line, if you do not have such a thing, for example, always if keys are available, fighting each other. And what fastest one will get the chance. Then some people may not get the chance to use the bathroom, right? So we need to address such a thing, that is the progress and the bounded waiting, the requirements. So all three, the mutual exclusion process means the selection will be done. It's not, so for example, if you, another example of such a progress is, so you, to decide the next one, okay, next person to use the bathroom, it will take forever, okay? If that selection is forever, then it may not, you may not get the chance to use the bathroom. So that the selection process should not be forever. So that is a progress, it's deadlock free. And such a waiting time should be finite time. So that is the bounded waiting time. So these three conditions should be considered when we design, when we consider the critical section problem. So okay, there are three different types of the solution that we discuss. First, we are going to start the software solution. Okay. The reason I'm using the slide for the synchronization problem is the first time it's not that simple, but it's not very complicated algorithm. So I'd better show the slide to understand the algorithm than try to my best to explain such a meaning of the code. Okay. So first algorithm, as you can imagine, we can use the key, okay, to access critical section. In this case, key is shareable, the shared data ton, okay. So for example, so we have in this case the two process case. So two process case, let's say the process I, process 0, and the process 1. Okay? So they are executing the different the instruction, but they are using the shared data I. Okay, so we define this is a critical section, also this is a critical section. to access, to use the I, shareable data I to enter the critical section. So this process need to get the key. That is the turn. Which means if turn is 0, okay, that means the process 0 is using I. The turn is 1 means process 1 is using the shareable data. Okay, so this is turn. So then, the entry section of this critical section model is while, I think I'd better write here. So what does it mean? If turn is equal to 0, which means process 0 can use the key. Okay? So then check this one. Turn is 0. It's not 0. Is it true or false? False. Okay? False means out of while loop, which means you can enter critical section. At the same time, for example, the P1 is running, then try to enter critical section. Turn is equal to 0. So why? Don't be confused. This turn is not equal 1 in the process 1 case. Okay? Because operating system has a general solution of the entry section. Okay? It's not fixed value of this part. So this part, good. This one, underline, will be changed based on the process. Okay? Algorithm is the same, but can be changed. For example, in this case, so turn is 1. 0 is not 1. Is it true or false? It's true, which means it cannot exit the while loop forever. Okay? It's an infinity loop. Okay? This one is waiting. It cannot enter the critical section. While turn is equal to 0. Then, if the process 0 is done, process 0 is done, and exit. Exit solution is what? Turn is equal to 1. Okay? Then this shared value is changed. Then this one will be 1 is not 1. Is it false or true? False. So which means out of exit the while loop and can enter critical section. Okay? Then you don't have to worry about the remainder section. Right? You don't have to worry about the remainder section because the remainder section does not affect anything for this synchronization part. So this is this is actually key. You can use one key. So when you are done, give the key to other. Okay? So this is one of the misunderstanding is this is a general solution, which means depending on the process, this value may be changing for each. But algorithm itself will not be changing entry and exit section. So operating system, keep watching. Keep watching means the while loop. This one. While loop, do while keep checking whether this one is entering critical section or not. In case the entering critical section, run the entry section to select the process, next process to enter. In case it's being used by another one cannot enter, keep asking until critical section is available. Okay, so this is the simplest way to solve the critical section problem. But however, we need to check whether this solution satisfies with the requirement. Not only mutual exclusion, some of the algorithm wait running forever. So let's see. The mutual exclusion, which means how many processes can enter critical section? How many? Only one. Okay? Only one. So it's good for the mutual exclusion. However, the progress, do you remember what is the progress? Selection process will not be forever. It's a infinity, at a finite time. deadlock free. It's not stuck. No matter how long it takes, the selection should be done. Do you think this algorithm is good for the progress? It's set bad, which means it's not good. Why it's not good? For example, no matter what happened, sometimes it may be happen, this is 2. Okay? But 2 is not there. Okay? Let's think about the 3 process case. So we have 0, 1, 2. So when this process exit, turn is 2. But 2 is not waiting. 2 is just remainder section only. Not accessing this one. Then, what about the P1? P1 cannot enter. This selection process sometimes may be infinity, okay? Until the process 2 would like to enter the critical section. It may be possible, okay? So because of that, if you really restrict term value 0 or 1, okay, in case of 2 process case, in case 3 process case, all of them should be run. So sometimes okay, but sometimes not okay. So because of that, the progress and bounded, it will wait forever until if the process 2 is not executed, or if process 2 is not entering the critical section. So in terms of the requirement, the progress and the bounded waiting time, so it is not the best solution. But it's simple. So in our real life, we are using this one, the mutual exclusion as the key. Okay? And also, however, so some of the public bathroom, you need to get the key, but if key is lost, nobody can use, right? Keep asking, just asking. So that is a simple situation. But algorithm 1 is this is just a simple case, okay, for your understanding. So this is this is actually the later you can understand that this one is timeline, okay, from this time. So time goes by, okay. Then this is a shared data. This is a explanation of the process 0. This is a process 1. So you can understand how the algorithm 1 is working. Any question? Is it practically used? Actually not used. It's as you can see, it's available only the 2 process case. Even the 3 one, this value will be assigned to which one? We don't know. It's a 2 process cases. It's just for your understanding. Another one is because this is the shared variable. You assign the process 1, process 2. You know the name, all of that. So instead, why don't we use the myself status of me? Okay, I'm not using. I'm using the critical section. I'm in the critical section, or I'm in the bathroom. In that case, true. Otherwise, false. True or false. Then you can check me whether this is true or false. If false, you can use, right? That will be better than this one, right? This one assign. So I got the key, then assign the next one. But this one, instead, my status is using or not using. So you can check the other. So whether the other is using or not using. Not using, then I can use. Okay? Then we don't have to worry about the unexpected case, like the turn 3 or whatever. Just check if he's using or not using. If everybody not using, then I can enter the critical section. So that is the entry section is this one, the flag I. So status of me. So true is I'd like to use. Okay? So I'd like to use the critical section. Then check the other, whether the other is being used. So J is, so as I said, this is a 2 process case. So I or J. So whether J is the using one. If so, we have turn, true, false. Turn, true, false. This is a I, and this is a J. So currently, so for example, J is being used. It's a true. And this one is a false. But when you enter the critical section, turn, change. I'd like to use the critical section at the bathroom critical section. Then check the other process. So when you check the other process, this one is a turn. J is yes, because it's a boolean. In case this one is true, means it's being used. Okay, so this is a loop. Until when? So exit is the flag I is false, which means I'm done. I'm not in critical section. Even I don't want to use the critical section. That means when this one is PJ is exit, turn J will be changed F. So this one is the F. F means so you can out of while loop, which means you can enter the critical section. It's very similar as the previous one, but it's slightly different. The first algorithm used T. We are using shared data. On the other hand, this algorithm used the status. You can check the status, not rely on the shared data, just checking the status whether the other process is in the critical section or would like to enter the critical section or not. Okay, so that is the algorithm 2. How many processes can enter the critical section here? Only one. So mutual exclusion is good. What about the progress and the bounded time? Probably not good. It's bad. Why it's not good?
Selection. Because many calls are waiting also to use the critical section. We don't know which call.
It's first two processes is okay, but when we have the multiple processes, may not. Okay. Also, another extreme case like the true. Unfortunately, same time two process is coming. Then change it. If nobody use right now. At the same time two process coming. Then change the value of the flag I'm using. Then both of them turn on the true. Nobody can enter. Okay. It may be happening. Okay. So that is if you are using multiple processor. Change the value, is it true? Then when they try to run the while loop, both of them are true, which means nobody can enter critical section. Okay? May not be happen if you are using the single process case, but in case of multiple process, it might be happen. So that is not a best solution, but mutual exclusion is okay, but it may not be. So that is algorithm 2. So algorithm 1, algorithm 2 is for your understanding. Practically we don't use. So first well-known synchronization problem solution is called the Peterson solution. So Peterson solution actually combine algorithm 1 and algorithm 2, which means we can check the key as well as who are waiting outside. So in other words, the turn and plus the flag together. That is the Peterson solution. So we are going to use the two variables. Turn is the key and the flag is the status. Okay. So it's nothing but algorithm 1 plus algorithm 2. So for example, so this is the algorithm for the process I. Okay? Which means process J has the, let's clarify. So this is a flag. The I is a true, and turn is a J, and the while loop. And flag J and turn is equal to J. Okay. Similarly, PJ has the entry section flag J is true, and turn is I, and Y, flag J, and actually this is I, and turn is equal to I. And exit section is flag I is equal to false, and flag J is false. So let's see. Good. So first, right now, flag I and J, both of them are false. Nobody entered. So both of them are false. Then turn is, let's say it's a default 0. It's a default value. So first, process I would like to enter the critical section, which means this is a process I. The flag I is we are going to set true, which means I'm going to enter the critical section. That is a flag I. And whose turn? Because I'm in, the maybe next one will get the key. So change the turn value into J. Okay, then check the while loop. Flag J is true. Flag J is the false. So it's not. Process J is not entering the critical section. It's a false. That means this is an end condition. So only either of them is false, we can exit the while loop. So it can enter. So no problem to enter the critical section. So right now, the process I is in the critical section. Then this time, this should be changed to true. Process J is entering. Then process J, the flag J is true. So I'm entering the critical section. Then turn is I. Because I'm in, so maybe the other will get the key. So, and while loop flag I is true. This one is true. And turn is equal to I, which means this is the while condition is true. Cannot exit the while loop because of this one. Running until you can exit. Process J is exit. When process I is done, I'm done. Flag I is false. Flag I is false. There's a flag. Flag I is false. This one is false. Then during the while loop, this one will be false.